Okay, so for Chapter 3, we're only looking at the first section. We're keeping our understanding of probability very, very basic. The importance for understanding probability for statistics, for an inferential course, is understanding random chance. Like when we have a result of an experiment or a hypothesis test, or even a confidence interval, and we want to answer the question of whether or not that result is significant. We need to start to build an understanding of probability and how random chance works. And so we look at a little bit of terminology here, your probability experiment, the outcome of a probability experiment. Sample space is all the total possible outcomes. And then the event, we'll look at what those outcomes look like when we put them together. So a little bit of terminology you definitely want to be able to commit to memory or look those terms up in your assignments as you go through them. But here we have a survey asking people their blood types, and they have 4 possible responses. Right? They have O, A, B, and AB. But then in addition to that, they could also be positive or negative. So the number of outcomes, which is kind of more important, we'll list all of them, but sometimes the outcome or the sample space, there can be so many of them that it's almost impossible to list them all. But if we can picture how many there would be, that's an even more valuable skill. So when we look at this, we see that we have the 4 options for O, A, B, and AB. And the idea here would be to multiply that by 2 for positive or negative. So we can look at that in terms of a tree diagram. But either way, we want to be able to picture that there would be 8 possible outcomes, even if we're not able to list them all. Certainly would be helpful to list them all when there's not that many of them. If the sample space is smaller, it can be helpful to list them all. Okay, here's another example of the tree diagram. I toss a coin and I roll a die. So now there's going to be 12 possible outcomes, 2 times 6. Right? So the simple event is 1 outcome. So I toss a head, I toss a coin, and then another simple event would be rolling a die. But if I have both of these happening, both events, that's no longer a simple event. Okay, tossing heads and rolling an even number, we can answer both of these by looking at the sample space. Right, tossing heads and rolling a 3, we can see that that's 1 out of 12. Right, there's one time where that happens out of 12. Tossing heads and rolling an even number, though, right? We have heads 2, heads 4, and heads 6. That's going to be 3 out of 12 possible outcomes. And we want to watch for the language of whether they say and or, right? Tossing heads and an even number will be different from tossing heads or an even number. Okay? So determine the number of outcomes in each event, then decide whether each event is simple or not. For quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. So since this is only 1 outcome, that specific machine part, we have ourselves a simple event there. Okay, you roll a 6-sided die. Event B is rolling at least a 4. So we think about this, at least a 4 means we could roll a 4, a 5, or a 6. It's not simple because there's 3 possible outcomes. Okay, our fundamental counting principle, and we'll come back to this in Chapter 4. I want to talk about this term a little bit. But in mathematics, when we talk about counting, we use the term a lot of times discrete mathematics. And the word discrete basically means hidden. And the reason for that is that most of our counting, especially more sophisticated ways of counting, are kind of hidden. And I'll give you the most basic example of that. If I told you I had 5 dozen eggs, you would know right away that I had 60 eggs. Not because you counted to 60. You didn't sit and count 1, 2, 3, 4, 5, 6. Right? Kind of just like in that last example. Even if I didn't see all 8 outcomes, I knew there were 8 there because I used the most basic form of hidden counting, which is multiplication. So when you're multiplying, you're really counting, right? The purpose of 5 times 12 is to know how many eggs I actually have. So multiplication is always a form of counting, and it's a basic one that we'll try to use here. So in this example, how many different ways can you select one manufacturer, of which you have 3, one car size, of which you have 2, and one color, of which you have 4. So we have 3 times 2 times 4, which would be 24 different ways. So first most basic way of counting. Okay? This example now we have several different directions we have to follow here. So you want to watch this if you come across this in one of the homework problems. We have an access code. It says how many different access codes are possible when, let's look at number 1, each digit can be used only once and not repeated. So that means the first digit, I have 10 choices that could live there, right? The numbers 0 through 9, those are 10 options. But I can only use that number once. So once that number gets picked, if you're picturing a giant tree diagram here, you'd have 9 numbers available for the next spot. And then 8 numbers for the third spot, and 7, so on. So the first one you would have 10 times 9 times 8 times 7. In the second one, if each digit can be repeated, that's the easiest one. It's just 10 to the 4th power. 10 times 10 times 10 times 10. 10 digits in each spot, right? We could have 0, 0, 0, 0 could be an access code. And the third one is the most specific, I guess the trickiest one here. Each digit can be repeated, but the first digit cannot be a 0 or a 1. So now, the first digit, there's only 8 options available there. But every digit can be repeated. So after I place that first digit of an 8, I have 8 times 10 times 10 times 10. So a little bit different. So the first one we had 10 times 9 times 8 times 7. In the second case it was just 10,000, and then the third case it would be 8,000. Okay. We have our classical probability or theoretical. This is where we're, generally this is kind of the world of probability that I usually live in and think about. And then empirical probability would just be where we accept data and we're going to have to believe that something has happened over many, many times or many trials, and that's the value we assign to it. All of these examples here are classical probability. We know if we roll a die many, many times, the outcomes that can occur. Okay. So the probability of rolling a 3 is 1 out of 6. Okay, the probability of rolling a 7, that's impossible, right? It's not in the sample space, so that's a 0. And then the probability of rolling a number less than 5, so that doesn't include 5. Less than 5 would be 4 out of 6, right? 1, 2, 3, 4. I try to write the sample space if I can in classical probability. Empirical probability, this is a lot of times what we'll have to go on in the news or reports. This is what has been happening. And it can be certainly very valuable, especially in trying to predict election results and those kinds of things. So here you have a pie chart, and we're going to use this as our probability, right? This is a little bit different from rolling a 6-sided die. We have data that's available to us, and we want to answer the question, what's the probability that the next adult surveyed read only print books? So I'm going to look at how many people read only print books, 578, out of the total. So the first thing I have to do is add all those numbers up, or I can look at the context here and see that there's 1,490 of them. So I have a total of 1,490. I'm going to take that 578 divided by 1490, and that's my estimate for that particular probability. A lot of times you'll have a table that looks like this, right? What is the probability the next user is 23 to 35? So I can see from 23 to 35, there's 312 of them. But if they don't give me that sum down at the bottom, they do it for me here, the 975. The first thing I would do is add all those numbers up and then find that probability using the table. So we have 312 out of the 975, and we would estimate that to be 0.32. Okay. The law of large numbers. This is why teams like the MIT blackjack team in the 90s could go to the casinos and make a lot of money. They wouldn't just sit down and play a few hands, and they also organize people to invest money in them, because in order for something like that to work, you have to be able to see it through in the long run. Notice, I could toss a coin 10 times, and I might get 8 heads. Okay, that's not going to be really unusual to get 8 heads in my first 10 tosses. That would be possible. It would be unusual to get 80 heads in 100 tosses if that coin is still fair. So for the probabilities to work out the way that we would expect them to in the empirical calculations, we have to be able to do something for a long time. And to be able to play blackjack for a long time, you need a lot of money. And you also need to be able to bet a lot of money at the right times. So they even had investors behind them to make that work for themselves. Subjective probability, this is just somebody's intuition or opinion. Not super helpful or valuable to us. So the probability you'll get an A on your next test is 0.9. That's going to be subjective. I mean, you're just basing that on your feeling. I can't imagine there being any other reason to have that belief. The probability the voter chosen at random will be younger than 35, we would use empirical. We can look at data that we've collected and see what proportion of people under 35 are voting generally, and we would estimate that. Okay. Here, the probability of winning a 1,000-ticket raffle is 1 out of 1,000. That is classical. You have one ticket. There's 1,000 of them. It's a 1 in 1,000 chance that you could win. Okay. Probability always has to be a value between 0 and 1. If something is impossible, cannot happen, it's a probability of 0. Something's guaranteed to happen or certain, it's a probability of 1. And then we have probabilities everywhere in between. You may see this notation, the E with that little tick mark next to it. That is read as E complement. It just means not E. The key about complementary events is that they always have to add up to 1. So if I take 1 minus the probability of E, I get the probability of E complement, or E prime. So they always have to add up to 1, and you can see we have 3 different incarnations of what that relationship might look like. I add them to equal 1, or I subtract one of them from 1 to attain the other. Okay, so randomly selecting somebody who is not 23 to 35. Well, we can take that 23 to 35 number that we already calculated, right? We have that already, it's 0.32. So if I want somebody who's not in that age group, I just subtract from 1, and that's going to be 0.68. That's your complementary event rule. Okay. Again, we can use a tree diagram to take a look at a sample space. Okay. Event A is tossing a tail and spinning an odd number. Event B is tossing a head or spinning a number greater than 3. So we want to be careful about the ends or the ors. So in event A, it was tails and an odd number, right? Tail and spinning an odd number. B is going to be tossing a head or spinning a number greater than 3. So let's see what that looks like. Okay. If we spin heads or a number greater than 3, then we have all of these tails in the sample space as well. T4, T5, T6. We have all of them, right? And we don't want to repeat any. I have the 4, 5, 6, 7, 8 over here with the head. So this is my whole entire sample space. That's the probability that it would happen. Looks like it's 13 out of 16. Okay. So what's the probability of getting your college identification number when randomly selecting 8 digits? Not great, right? We have a whole lot of choices here. So the fundamental accounting principle says there's 100 million different possible ID numbers. So yours would be 1 out of 100 million, right? You can repeat numbers.